motion. The purpose of this lab was to observe an object or projectile being thrown and observe the object's observed positional data and compare it to a computational model based on Newton's second law of the momentum principle. For this lab, the model of observed values was created in the tracker app, and the model of the predicted values to show the effects of gravity or gravity plus drag on a paper ball will be done in GlowScript. This lab should help demonstrate Newton's second law, which states that the net force equals the change in momentum over the change in time. We used a computational model based on the momentum principle because the principle states that the net force acting on an object, or in our case gravity or gravity plus drag, causes a change in an object's momentum over time, as shown by the equation on the right. Here's a brief overview of what my result from the lab will look like. In this lab, we threw a wadded up ball of paper in an arc-like motion using a meter stick for calibration. The system for this lab is a wadded up piece of paper, and some of the surroundings include the earth, which creates gravity, and the air, which creates drag. The first step of this lab was to record a video of the paper ball being thrown. The second step was to create an observational model using tracker, which you can see on the left, and then using the first two rows of data, we were able to compute the initial position and initial velocity as shown on the right. And the third step of this lab was to create a computational model using GlowScript, which shows the effects of only gravity acting on the paper ball. The highlighted lines of code are the lines that we edited. Ball mass was measured to be 0.00375 kilograms. The initial position of the ball and the initial velocity of the ball were calculated on the last slide. Delta T, which measures is 1/30th because that's the size of each time step, or the time between each frame of the video we took. For this set of code, B is going to be 0 because we do not want to include the force of drag. The code is going to run until while T is less than 0.50, and then the force of gravity is just the vector 0, negative mg, and then 0, and then Fnet is just going to be Fg for this set of code. And then to update the velocity of the ball and position of the ball, we just use the velocity update and the position update formula. Next, we created a computational model using GlowScript that demonstrates the effects of gravity and drag acting on the ball. As you can see, most of the lines of the code are the same, except for we included F drag, which is basically this formula on the right that's being put in to F drag, and then Fnet is now Fg plus F drag. Everything else is the same except for B equals 0.001. Here's some of the graphs from our computation models. On the left is just gravity, on the right is gravity plus drag. Here is the data from each of our models. The blue line shows the observed data, the red line shows gravity, and the yellow line shows drag plus gravity. As you can see, drag plus gravity is smaller than gravity because the drag will slow down the paper ball and it won't go as far in the X or the Y direction. The possible errors for our data include other external forces such as like a slight breeze maybe, or other possible errors could be human error, which could be misclicking the ball on tracker and not clicking its exact location. And then, do any of my graphs predict a terminal velocity? On the right, first of all, terminal velocity is when the net force acting on an object is 0, which would mean that the velocity goes unchanged. As you can see, the graph on the right has a constant line, so velocity doesn't look like it'll be flatlining at any point, so this graph does not predict a terminal velocity. On the right, however, the gravity plus drag graph looks like it will you can see a slight curve which shows that it will be flatlining eventually, which predicts a terminal velocity. If the object was thrown straight up with the same initial velocity, would it take longer to reach y equals 0? As you can see, I derived the velocity update formula to get t equals 2 v sub o over g. This basically shows that the time it takes for y to equal 0 as the object comes back down is proportional to the initial velocity of the ball. Since we're throwing the ball straight up, all of the initial velocity is concentrated in the y direction, so the initial velocity in the y direction would be greater if the ball was thrown straight up compared to our lat. Because of this, and because we know that the time it takes for the object to reach y equals 0 again is proportional to the initial velocity, we know that if the ball was thrown straight up, it would take longer to reach y equals 0 again.